To introduce our second faculty speaker, Professor Purnima Padmanabhan, who is an assistant professor at Rochester Institute of Technology in the Department of Chemical Engineering with an affiliation in the Department of Chemistry and Material Science. So her research interests are in the area of thermodynamics and rheology of soft materials comprised of polymers and colloids, in particular in developing rational computational approaches that design materials with desired composition and length scales. So look forward to the talk.
Okay, can you all see my screen?
Yep.
Okay, great. So thank you very much for the opportunity. I'm really excited to give this talk. It's on the rational design of the gyroid morphology from self-assembly of copolymers. So I want to right off the bat acknowledge my students who do the work. So Natalie Buchanan is a graduate student. She's also here attending the talk. And Liana Ketchum is an undergraduate who is a senior this year, and she's applying to grad school. So if she does apply to your school, watch out for her, she's great. And so again, we've had the COVID for the entire year. So my newest photo is from December 2019. I also want to acknowledge the research computing, which I utilized to run, to collect the data. And part of the work is also from my work during grad school at Cornell University with Fernando Escobedo. Okay, so we all know that block copolymers self-assemble, but I'm going to give you a 2-slide summary of how the thermodynamics of this works. So block copolymers are 2 different polymers connected end to end. And so for understanding the physics of it, we can just smear this out as a red and a blue region that sort of repel each other, and we label it as A block B. So typically, if you have a polymer blend and these 2 types of molecules, A and B, repel each other, you will have macrophase separation. This is almost like water and oil separation, except now you have a polymer, so it looks like spaghetti separation. But if they are combined together, what happens is they can only microphase separate. So within every molecule, it forms nanodomains or microdomains, and then these domains arrange in space, and you get all these really nice pattern structures. And so the thermodynamics is going to determine the structure. And the main way we understand the self-assembly is on the y-axis, you have the enthalpic strength, and the x-axis, you have the fraction of B here. And so again, you can have disordered micellar structures, cylinders, gyroid, lamellar structure as you go left and right in the phase diagram. And as you go up and down in the phase diagram, that is, you modulate temperature or repulsion or chemistry, you can go vertically in the phase diagram, right? So I'm more interested in this gyroid morphologies, which are these which is in a really narrow region in the phase diagram. And so why do we care about the gyroid networks? Because these have been shown theoretically to have really good optical properties. So in butterfly wing scales, these contribute to structural color. And then you can also design materials which are chiral beam splitters or that have negative refractive index. So this is, again, a very futuristic application, but these materials are also very porous and nano ordered, so you can have really good transport. For example, these are used in solar cells and battery devices in the past. But again, coming back to the phase diagram, it's bad news. You have this entire phase diagram, but the gyroid phase is only stable in 5% of the region. So practically, this narrow thermodynamic stability means, any inaccuracies in mapping this exact parameters will lead to incorrect synthesis, right? And once you synthesize something, then you cannot really move in the phase diagram left and right. You can only change temperature and you can go up and down, right? So the only leverage that you have in a practical sense is vertically, not horizontally. Okay, and more serious issue is, I cannot get a gyroid at 25% volume fraction. So if some application calls for 25% volume fraction or composition, then I really cannot access that, that morphology. Although we have 5% region in the phase diagram that the gyroid is stable, the proximity of metastable phases and the defects typically ends up being useful. It's really a thin line, and it's really, really hard to access this morphology. And so my work is focused on how can we avoid these pitfalls and how can we actually access the gyroid morphology. And what practically we can think of, we aim to land somewhere close to the gyroid phase in the phase diagram, and then induce a structural change and go left or right. And again, we can use thermodynamic modifiers to modify the free energy and go in the phase diagram. So, you know, the parameter space becomes really large the more components or species you start adding. So we want to think a little bit carefully before just playing around with the large parameter space. Again, so we look at the thermodynamics. So free energy is a function of both the enthalpy and the entropy. And so the enthalpy is based on the chemistry typically and the affinity to each of the blocks. You know, we can think of solvents where it prefers one or the other phases, or you can add co-surfactants or other polymers that prefer the interface. And then you can also change the entropy by adding the second component. So there's two kinds of entropy the moment you add something. One is the mixing entropy, and the other is the conformational entropy. So again, alpha here is the relative size of the modifier to the copolymer. And again, you can think of different length scales for the modifier, and that is going to impact the mixing entropy. And so typically, if you have smaller components, it's easier to mix. And if you have larger components, they tend to demix. But on the other hand, larger components really give you conformational entropy. So a really tiny solvent molecule is not going to impart any conformational entropy. But if you start adding a polymer, you start getting more conformational entropy. So here we have all of these different knobs to turn. And then, of course, you can also add this modifier in different compositions or in different volume fractions. So yeah, so we have really, really tons and tons of variables to play with. And to summarize these, we have the size of the modifier, whether it has any intrinsic structure or whether it has conformational entropy or not. And then you have the chemical affinity and then the composition. Okay, so I'm going to give you a really quick summary of 3 different stories. And so let's say we wanted a gyroid morphology at a specific volume fraction. And you know, we're most likely to land at the lamellar phase when you create a block of polymer. And so one strategy might be to use 2 solvents that kind of change the effective volume fraction of the phase, and then you can sort of move towards the left in the phase diagram and get the gyroid morphology. Or if you land on the other side where you synthesize a cylinder, you want to choose a co-surfactant that's going to help you move to the right in the phase diagram and decrease surface tension and basically increase your curvature, right? And the third one is, you know, we want a gyroid, we just want to make it more stable. And so if you can get really close to this 33% composition in synthesis, then we can add another selective polymer that would stabilize the gyroid phase. Okay, and now I'm going to show a little bit of example I'm going to show one of these examples right now. Okay, so I use particle-based simulations. So we have this abstract block of polymer. We use a bead spring model. We use a soft potential that allows rapid nucleation and phase separation. So we studied it using dissipated particle dynamics, and depending on the problem we studied, you know, you can have 18 mer to 60 mer. We have harmonic springs. And one issue I will highlight with particle-based simulations is that the simulation box size really influences the morphology. So to overcome the situation, I studied a range of different box sizes, and we try to get to identify the location of the phase diagram with the highest propensity for forming these gyroid morphologies. Right? And we can also perform free energy calculations. They're a little more expensive. They're not always performed, but I have performed these in the past in a couple of scenarios. But really, the reason we care about particle-based simulations, or the advantages, you can really ask questions and hypotheses about the rational design approach. Right? So we can measure the end-to-end distances, which sort of gives an idea of the conformational entropy. We can look at the volume fraction distribution within the morphology. Again, it gives an idea of the mixing entropy in the system. And then we can also characterize the topology, which I'll talk about a little bit. And topology becomes particularly important in gyroid morphology. And again, I'm going to quickly talk about what is called the pattern frustration hypothesis. Right? So again, based on thermodynamics, we just know that we need to minimize free energy and we'll get a stable structure. But just thermodynamics doesn't tell us anything about how to rationally design these structures. But to summarize, the free energy in terms of rational design, our energy and geometry come from the surface tension or the chi-n parameter, and the entropy comes from the conformational entropy of the polymers. Right, so if you had a gyroid structure, which is a network, you really have tubes connected by junctions or nodes, and typically the junction size is much larger than the tube size. And so what happens is if you want to arrange molecules within this geometry, one of them has to stretch a bit, and so that leads to a loss of conformational entropy. And if it doesn't stretch, you don't have uniform mixing, so you lose mixing entropy. And if both blocks try to stretch a little bit, then you lose your geometry, and again, you sort of lose your structure. So this is one of the reasons. These are one of the reasons that the gyroid structure is really unstable in the phase diagram. And so we want to come up with strategies to mitigate this pattern frustration, and you can do it in many different ways. And one of them could be you take a different homopolymer and you sort of that prefers to go into one of these nodes. Or you could have a second strategy where you have a short co-surfactant that shares the interface. So what happens is when you blend these two different polymers, they occupy the same interface, but then the entropy in the blue phase is much larger because the longer chain has more wiggle room that's available. So again, we can think about this tie line approach where you start with a cylinder phase and you add a shorter surfactant which forms a lamellar phase. And again, if you change composition, I should be able to draw this tie line and get gyroid somewhere in between. So again, we did that in simulations, and we indeed get cylinder on one extreme, lamellar on the other extreme, and the gyroid in between. But when we get the gyroid, we also get defective cylinders, and so we calculated free energies. And you can see that the free energy difference is really, really tiny, and these could be metastable. So we probed and we went and looked at what the molecules were doing. And again, you can see these little defects and non-homogeneities that are there in the bulk phase. And then if we think about our hypothesis that it's going to share the interface, and we actually do the measurement, we see that it actually forms two different interfaces. You have this outer interface made by the longer chain and the inner interface made by the shorter chain. And so the hypothesis that this would relieve pattern frustration didn't really work when you add the co-surfactant. Okay, so again, to summarize, we can get a gyroid at approximately 25% volume fraction, although it may be a little bit metastable. And we got this by using this tie line approach. We start with a cylinder block copolymer, we added a lamellar block copolymer, and at some intermediate composition, you should form the gyroid phase. And again, this enthalpic tie line approach works partly, but really you need entropy to actually mitigate metastability. Okay, so that was the second part of my work during my PhD, where we took this block copolymer and added a homopolymer. And now you can see that we computed free energies, and we see that the gyroid phase is purely stable. There were no competing structures that were found. And then we can find the optimum bulk size, the unit cell size, and we can go all the way up to 50% in volume fraction. So if you have just a binary system where you have AB block copolymer, depending on the surfactant you add or the polymer you add, you can go from what was just 33% gyroid to something all the way down to 22%, all the way up to 53%. It's easier to go right in the phase diagram because you are adding entropy. It's a lot harder to go left in the phase diagram, but it is actually possible. Okay, and so that was the story for a double gyroid network. And so can we do the same thing for a single gyroid network? And so recently a paper was published where you could get a single gyroid by using a chiral block copolymer. But again, it's only stable for a narrow composition window. In this talk, I'm going to give a different strategy where it's a chiral block copolymer, but we're trying to get the alternating gyroid or single gyroid at a really large composition window. Okay, so again, we had three chemistries. So the parameter space increases by a lot. So typically we'd have two repulsion parameters, chi-n and Fa, for a diblock. But when you have a triblock, you'll have 5 design parameters. So you have 3 repulsions and 2 compositions, right? And so, we really want to narrow down this parameter space when we are doing rational design. And so one simple way to do it is to just look at the idea of frustratedness in terms of enthalpy and architecture. So on the extreme left, A and C mix, and so that means the polymer doesn't want to phase separate, like the end blocks want to be co-located, and so that will not result in phase separation, and that's called the frustrated type 1, and we don't want that. You could also have frustrated type 2, where the end blocks repel each other, but the middle block, doesn't really help with phase separation. The third type is a non-frustrated, where the end blocks are extremely repulsive. And so the middle block sort of mediates this repulsion between the end blocks. And so that's really the parameter space that we want to look into. And so again, just to tell you how complicated this phase diagram would be, you can change the chi parameters and you can end up with many different types of gyroids, and you really want to be careful what kind of gyroid you want. So if you have really low repulsion, you end up with a single interface. If you have if you have high repulsion, you have two interfaces, right? So we get all of these different 10 kinds of gyroids, and we want to focus on what's on the rightmost. So here, chi AC is very, very high compared to chi AB and chi BC. And people have studied this with ISO tri-block copolymers. They have studied the phase diagram, and we are repeating this for particle-based simulations. Okay, and so I'm going to quickly summarize the phase diagram. You have micelles, we find cylinders, we find network structures, we have the B majority network structure, and we have B minority network structure that are both separated by this lamellar phase. And the question really that we want to answer is, how do we bridge these two, the gap between these two network phases? It'll be really nice if we can get a network in a really large area in the phase diagram. Right, so again, we follow the similar approach. We add a selective homopolymer, and you can add the selective homopolymer of different lengths. And as you go from alpha is 2/3 to 4/3, we also remember that you're going from a wet brush to a dry brush transition, and you actually see a difference in behavior as this happens. So we went and added homopolymer, different compositions, and we still get the alternating gyroid. And one thing to note is that we go from a symmetric alternating gyroid to an asymmetric alternating gyroid. And again, these are really useful when you want to tune the morphology. And so now we went and characterized the topology by looking at our simulation, dividing it into voxels, and finding, assigning a type of the voxel based on the volume fraction. And then, we can also characterize the topology quantitatively by saying how far is a voxel from the interface. And so we can do this, and we can plot isosurfaces. And you can see that when you have a pure block copolymer, it's pretty defect-free. You can see uniform gyroids, and you can see uniform layers between the subsequent layers, like an onion shape. But if you add a homopolymer, it starts getting, you start seeing some defects. We still get gyroids at much, much larger domain sizes. So we can quantify these domain sizes. So on the y-axis is the maximum size of the gyroid, and the x-axis is the composition. And again, this is dependent on the alpha of the domain size. So again, if you wanted to reverse engineer and get a gyroid at some particular composition, we have a way that we can go back and pick the correct homopolymer that we want to add, and sort of have this map to be able to do this. Okay, and then after we characterize the topology, we also want to correlate the end-to-end distances, because again, the end-to-end distances are what contributes to enthalpy and entropy. Sorry, is going to contribute to entropy. Right, so we can now calculate the block center of mass and identify the end-to-end distance, and then go back to this topology map and figure out how far away from the interface block is and what its associated end-to-end distances. So here we looked at the occupancy. So if you have a pure block copolymer,
1 minute left.
Thanks. So if you had a pure block copolymer, most of it is occupied near the interface, the center of mass. And then if you looked at the end-to-end distance, you can see that as the block goes away from the interface, it actually stretches, and this makes sense. But when you add the homopolymer, what we see is the homopolymers are located deeper in the network, and so that relieves some of the pattern frustration. And if you plot the end-to-end distances, it maintains its bulk conformation. So really adding this additional conformational entropy is what I believe really helps stabilize the alternating gyroids at intermediate combination. Okay, but again, you cannot do this willy-nilly. You cannot add a very, very long homopolymer. As the size of the homopolymer increases, or as they go from the wet brush to a dry brush regime, this benefit in conformation entropy starts getting weaker. And so really we want to use conformation entropy, but use it in a smart way. So we want to add a homopolymer that's smaller or the same size as the block length. And then again, the thermodynamic Thailand approach works sometimes, but it doesn't create very, very stable phases. And again, we have been able to successfully bridge the gap gyro of the networks in tri-block copolymer and increase the domain size or the volume fraction in a diblock copolymer. And I'm just gonna leave you with a tiny bit of joke. Self-assembly can be hard, especially if you're used to assembling IKEA furniture. And then rational design makes it possible, and entropy is your friend, and the piece is that it's better than customer service. So thank you very much. I'm happy to answer any questions.
Thank you, Professor Padmanabhan. That was a fantastic analogy at the end. I might unceremoniously steal it for future talks. I enjoyed it. Our first question comes from Professor Jayaraman at the University of Delaware, and she says, nice talk. Thank you. Have you looked at the effects of additive architecture, such as the AB multi-arm star copolymers or hardness, like AB-coated Janus nanoparticles, on the widening or narrowing of the gyroid phase? There's a second part, but I'll wait until the first part is answered.
That's a great question. We have not looked at that. I know Fernando Escobedo has worked a little bit on that. He has looked at branched side chains in hard particles, and so again, you do see a stabilization of the gyroid phase. And again, so the technique that I use is really a soft DPD kind of potential. So I haven't looked at more of the hard especially nanoparticles is much harder to do using DPD. But I mean, we could of course do the same thing. The methodology will apply whether we have DPD potential or Lennard-Jones potential. So it's certainly possible, and you can certainly apply the same algorithms to look at the conformations. And again, that should not be a problem. So again, I haven't looked at it, but there's no reason that won't work. My goal is start really simple, try the easiest thing first, and go from there. So.
Yeah, that was great. You actually answered the second part in your answer, okay. The first part, because she was asking a follow-up, would DPD handle the ladder well? And you answered that probably not for a Janus particle, but that was really fantastic. I have a couple of questions if others don't, that give a little bit more time for others to type theirs in. Really quickly, I saw the excess free energy that you calculated on slide 12. I believe it was for just the die block case.
Yes.
And I wanted to know, is that on a per polymer basis? So the beta A that you have there, is it per polymer or per monomer? So that is something that, thermodynamically, your error bars are fairly big, so it's hard to tell if it's actually significant. So, but in a massive melt situation, you could have a phase separation similar to what you see in colloids when you have the FCC versus HCP lattice, where the free energy is an extremely tiny fraction of a KT per particle, but when you get to the system as a whole, it's so vastly preferable that that's the type of thing you see.
Right. Yes, it's possible. And I will note, so I didn't have time to go into free energy calculations. So this was way back in 2012 when we used to use particle insertion methods to calculate free energies. Later, we found that this method isn't really accurate because, again, it has large error bars, and it does a poor job of finding the optimum unit size. So later in 2016, I developed a method method based on thermodynamic integration. And so now you can see really it captures this box size dependence really well. And we can also compute the, we can also infer the ideal box unit cell dimension. So here that's about between 23 and 24 sigma. And so here again, so the thermodynamic integration method is just a little bit better. And here now you can see the error bars are smaller, and you can actually see the difference between the stable phase and the other one.
Very, very cool. Yeah, I have a distinct interest in free energy calculation, so noting some of those details is really cool for me. You did use DPD. I don't see another question here, so I'll follow up with one other question I had. Since you used DPD for this, did you attempt in any way to examine formation dynamics from just a kind of from a random melt state, or?
So these were all started from a random melt state.
Okay. And so did you characterize the dynamics as well, or just the sort of free energies and the types of things that formed in the stable configuration?
I have looked at it in the past. I don't have the data right now. It's really, it nucleates really quickly. And again, it was just a small, interesting plot for me. I didn't really look at it in details and really look at it in detail. But it happens in less than 1% of the total simulation runtime.
Oh, wow.
So I'm not really, really looked at that stuff. Yeah.
Okay. Well, thank you very much.
Yeah, you're welcome. Yeah.
No, thank you very much. That's fantastic. I don't want to monopolize things. If there's another question in the room, please please type it briefly in. I'll give a couple of seconds to the room to see what could happen.
So we usually open up the floor at this point for folks to turn on their videos, and we even give them access to unmute.